So this is our last bit that we're going to talk about in section 5.5. And we're talking about the area of regular polygons. Now we wrote down a formula. We labeled some parts in our flip book the other day. So I just want to go over that again, just to re-emphasize that and make sure that everybody has that. So I think in your flip book you have a pentagon, and you also have an octagon. So you can label either one, or you could label them both actually. So we have a point here that in our center, and we're going to put in this segment and this segment, and we're going to talk about both of these today. This segment is the apothem. So we name that the apothem of our polygon. And this segment, the apothem, goes from the center to the middle of the opposite side. So each of these segments is congruent. It cuts the side in half. And remember, we're talking about a regular polygon. So what does regular mean again for a polygon?
Angles and sides.
All the angles and all the sides are the same. So each angle, each side has the same length. So the apothem goes from the center at a 90-degree angle to the middle of one side. And this segment that goes from the center to one corner, one vertex, is the radius. And it's the same for any type of polygon, a triangle, a square, a rectangle, any polygon. This is the same. And we set our formula, the area equals 1/2, let me write it a different way, equals the apothem times the perimeter divided by 2. And the way we usually write that is AP divided by 2. And that's the same as saying 1/2 AP. Dividing by 2 is the same as saying 1/2. Now for any shape, how do we find the perimeter? You just add up all the sides. So there's not really a formula for the perimeter. You're just adding up all the sides. So we'll do an example in just a second. But let me go over why the formula looks like this, where this formula comes from. And I talked about it just a little bit the other day. So for this one, we'll draw, and you don't have to draw this picture in your notes. I just want you to have an idea of where the formula comes from. So what we're doing here is I'm going to take this is the center of my regular polygon, and I'm going to draw in this, and I know I haven't drawn it perfectly, so you have to bear with me there. And I'm going to draw in this. So here's my apothem. I'll call my apothem A. Now for this triangle, I'll highlight the triangle in green. For that green triangle, what part of the triangle, what have we been calling this part of a triangle when we draw a segment in a triangle like that? The what? It bisects, so this is a regular triangle, so it bisects it. What segment goes at a 90-degree angle from one side to the opposite vertex? What do we call that? What do we find using that segment? What? The height. There we go. So we thought about it a little bit. So this is the height of the triangle. So the apothem is the height of the triangle. Well, here's one side of my polygon. What part of that of the triangle is this side of the polygon? And think less, we're not special right triangle, but just in general. So if this is the height, what did we call this side? The base. So this is the base. So the base of this triangle is one side of the polygon. Well, so the area of my polygon is the area of this triangle is the base times the apothem. I can divide this pentagon if I draw in some other radii. We'll do it in red. There's another one of those triangles. There's another one. And there's a couple more. So I have a total of 1, 2, 3, 4, 5 of those triangles. They're all the same size because we have a regular polygon. And we said the area of one of the triangles was the base times the apothem divided by 2. That's the area of one triangle. And I have 5 of them. So to add up all 5 of them, I'm going to multiply the area of this one times 5. Well, if the base is one side of this pentagon, and I multiply the base times 5, I'm getting this side, this side, this side, this side, and this side. What part of the pentagon does 5 times this base give me? That gives me the perimeter. I have this side, I have this side, that side, that side. So I'm counting up 5 of those sides. So that's the perimeter. So this formula is the perimeter times the apothem divided by 2. And these are just, up here I switched the order of those two. Well, so what I'm saying is this is where the area, the formula comes from, is looking at the area of one of these triangles and then just adding 5 of them up. So for a pentagon I would have 5, for a hexagon I would have 6, for a 7-sided polygon I'd have 7. So what we're doing is dividing our polygon into triangles and then just adding up the areas of all the triangles. So I wanted you to see that the formula comes from the formula for the area of a triangle. I'm just adding a bunch of them up. I have 1 for each side of my polygon. So that's where the formula comes from. And you'll see this a lot in geometry, a lot in math. If you go further in math, the idea of dividing a shape into triangles, using triangles to solve a problem, because triangles are really our simplest, kind of most friendly shape, and we know a lot about them. So a lot of times a problem will turn out to involve dividing our shape into triangles and then using what we know about triangles. So I just wanted you to see that this comes from finding the area of triangles and then just adding a bunch of triangles up. So let's look at a couple of examples using our formula, and we'll also talk about, we haven't really talked a lot about the radius. We use the radius as the side of these triangles, but what happens if we have the radius and not the apothem? So we'll talk about that also. Okay, so a couple of examples. So for this one, we'll start out nice and easy. We have a pentagon, and we're going to say that I'll draw in the apothem. And this is 8 centimeters. It's supposed to be an M. And this is 12 centimeters. And we want to find the area. Well, we know our formula, area equals 1/2 the apothem times the perimeter. So what do we need to figure out here that we need to plug into our formula? We need to figure out our perimeter. So the perimeter, how do we figure out the perimeter here? If one side is 12 centimeters, How many sides do I have? 5. So what would I do to figure out the perimeter? 12 times 5. 5 times 12, which gives me 60 centimeters. So I'm just adding up all the sides. We were talking about regular polygons, so all the sides are the same. So now I just plug my numbers into my formula. The area, I'll use a capital A for area, equals, and I can rewrite this. We can write 1/2 AP for AP divided by 2. The apothem is 8 centimeters, and we're multiplying by 60, and we're dividing by 2. And when I multiply that all out, I get 240 square centimeters. Our units for area are always square units. Questions on that example? So for a regular polygon, we need to know the apothem, and we need to know the perimeter. Perimeter, add up all the sides. The apothem goes from the center, 90 degrees, to the middle of one side. Well, let's look at an example where we have the radius. Where we have the radius and not the apothem. And this will tell us what happens or why we might need the radius. So we'll do that down below here. So we'll do a pentagon again. It's the same process for any shape. I'm just happen to pick pentagons today. All right, so for this one we know that this is 11.88 units, and this is 14 units. And again, we want to find the area. Now this problem is where a lot of people will make a mistake because they'll think, oh, this is the apothem. Remember, the apothem has to go from the center to the middle of the side. So we have the radius. So let's draw in the apothem. I'm going to draw it in like so. There's my apothem. We need to figure that out. And this is a 90-degree angle. What can we do to figure out this apothem? Anybody have an idea? Preston? Do the triangle. We have a little right triangle. What do we know that the apothem does to this side? Right. It's a right triangle, and it cuts it in half. We said the apothem goes to the center of the side. So if the whole side is 14, how long is this piece of the triangle? That would be 7. Now I have a right triangle, and I have two sides of the right triangle, so what can I use on this right triangle? Pythagorean Theorem. Pythagorean Theorem always works on right triangles. So what side is 11.88? Is that
C?
That's C. That's a hypotenuse. It's the longest side. So this is C. We already have A, so we can call this side B for our Pythagorean Theorem. So we know that A squared plus 7 squared equals 11.88 squared. So A squared plus 49, 7 squared is 49, equals, and I'll plug 11.88 into my calculator to find what that is squared. Where's my calculator? There we go. So I'm going to put 11.88, square that, and I get 141.13. Subtract 49 from both sides. I get A squared equals, and I put that in my calculator, subtracting 49, I get 92.13. So the apothem, take the square root of both sides to undo that square. So the apothem comes out to be, take the square root, I get about 9.6. So the apothem equals 9.6. So now I can plug my numbers into my formula, but I need one more piece. What's the other part that we need for my formula? We need the perimeter. The perimeter is going to be, how do we find the perimeter here? 14 times 5. One side is 14. We have 5 of them. So the perimeter equals 70 units. 14 times 5 is 70. So now I can plug my numbers into my formula. The area equals the apothem, 9.6, times the perimeter, 70, divided by 2. Plug that all into my calculator, and I get the area equals 336 units squared. So when I have the radius, I have to use the Pythagorean Theorem to figure out the apothem. I know the apothem cuts the side in half, so I can use the Pythagorean Theorem to find the apothem if the problem gives me the radius. So sometimes the problem will give you the radius, sometimes the problem will give you the apothem. You have to be careful with those two. Any questions on those examples? All right, one last thing we need to talk about, and that is hexagons. Because hexagons are special. Hexagons, I put my C and my I together, S-T-E-C. I tried to get one letter to equal 2. Hexagons are special. So let's draw a hexagon, and we'll think about a hexagon for a second. And we'll figure out why they're special. So there's my hexagon. There's my center. And I'm going to draw in a triangle up here. Does anybody remember, we talked a while back about the central angle of a polygon. And we figured out how to figure out the measure of a central angle. So this angle is going to be the central angle. Everybody remember how we figured out the central angle of a polygon? Yeah. You're close. You're thinking of an interior angle, so that's one of these. So it had you're on the right track. So it had to do with going all the way around. How far is all the way around? 360. And how many sides do we have here? 6. So if each of these is 1/6 of the way around, our central angle is 360 divided by 6, which turns out to be 60 degrees. So now if I draw in, so this angle is 60 degrees. If I draw in my apothem, like so, and I draw in my radius, like so, and I'm going to draw in my other radius over here. What does the apothem do to this 60 degree angle here? Cuts it in half. So that makes that a 30 degree angle. What does that make this angle? That makes that a 60 degree angle. So inside a hexagon we have a 30, 60, 90 triangle. So if I know the side length, say the side length here is 10. The side length of the hexagon is 10. what would be the small piece of this, the small side of this triangle? 5. And using what we know about 30, 60, 90 triangles, how long would the apothem be? How do we go from the short side to the long side? Multiply by the square root of 3. So the apothem would be 5 times the square root of 3. So for a hexagon, because we have this 30, 60, 90 triangle inside, all we have to know is the side length, and we can figure out the apothem. So we're going to, you should write this in your flip book. For a hexagon, and this is for hexagons only, the apothem equals the side divided by 2 times the square root of 3. So for a hexagon, all you have to know is the side length, and you can figure out the area because of this 30, 60, 90 triangle inside the hexagon. So the apothem is going to be the side length divided by 2, and you multiply that by the square root of 3. And we can find the apothem. We can figure out the perimeter by adding up all the sides, and we're set. So that's what makes hexagons special. We know the side length, we can figure out the area because we can figure out the apothem with this little 30, 60, 90 triangle inside. So let's look at an example using this. So we have a nice special hexagon here. And we know that the side length is, let's say 14 centimeters. And we want to find the area. So we know that the area equals the apothem times the perimeter divided by 2. So we need to find two things. We need to find the perimeter. How are we going to find the perimeter? 14 times 6. We know one side is 14. We have 6 sides. And 14 times 6 is 84. So our perimeter is 84 centimeters. And our apothem, because hexagons are special, we can figure out the apothem just with the side length. The apothem is going to be 14 divided by 2, and we multiply that by the square root of 3. So the apothem is 7 square root 3 centimeters. And now we can plug this into our area formula. The area is the apothem, 7 square root 3, times the perimeter, times 84, divided by 2. And I'm going to plug that into my calculator, and I'm going to leave it in simple radical form. And I get that my apothem, or my area, is 294 times the square root of 3 square centimeters. I've multiplied 7 times 84 and divided by 2. My numbers outside the square root I can multiply and divide, and I leave the numbers inside the square root alone. So I multiplied 7 times 84 and divided by 2 to get 294. You get 294 times the square root of 3 centimeters squared. Questions on that one? And we mentioned it the other day, really quickly, that we can do the same kind of thing with an equilateral triangle. There are 30, 60, 90 triangles hidden inside equilateral triangles also. Let me draw a couple of equilateral triangles here. So if I draw the radius and the apothem of an equilateral triangle, like so, this is a 30, 60, 90 triangle. So inside an equilateral triangle. And if I divide this equilateral triangle in half this way, I also get a (30, 60, 90) triangle. So there are 30, 60, 90 triangles hidden inside equilateral triangles. So if you have a problem with an equilateral triangle, you can use these 30, 60, 90 triangles that are inside equilateral triangles also. So any questions? So we have one more area formula. Some more places where we can use 30, 60, 90 triangles and the Pythagorean Theorem. But we're just doing more of what we've already learned how to do. Mainly we're working with triangles. We're working with area of triangles and special triangles since we know about triangles. Okay.